good enough? Yep. Okay, welcome back everybody on a hot Boston day. I can't believe I just I put my winter gear away like 2 weeks ago. Now it's 87 or something. Okay, so we spent the last couple lectures learning about two things really. Limit cycles first. What was the ways to extend our thinking from long trajectories or even points and trajectories into cycles, and that required a few interesting new ideas like orbital stability, right? Systems that are not stable in along the orbit, but they're stable to the orbit. And then we talked about hybrid dynamics, so collisions with the ground, contact. And last time I gave you this picture that I'm going to continue to build on today, which I think is a very, it's what I always go to. It's my go-to picture of thinking about what does it mean to have a smooth dynamical system that is punctuated by discrete events, where those discrete events are defined by guards in the state space and reset maps, how the state evolves once it comes into contact with that guard. For instance, the foot hitting the ground is a condition like the foot position here, and then this tells me what the state of the system is after that contact. Last time we did the trajectory optimization version of that, right? And we said we did hybrid trajectory optimization. And we said it's actually not that hard, both in the periodic case or in the hybrid case, to think about this as an optimization problem we already know how to write for the continuous, another optimization that we know how to write for the continuous here, and they're just linked. The initial conditions of this are connected to the final conditions of this by one extra set of linking constraints, right? And we solve that, we have to solve them simultaneously, because if you think of this as somehow the error between those two being connected as a defect that the constraint that the optimization has to solve, then it might change the solution of this trajectory in order to match up with this and vice versa. So you solve them all as one big optimization, but especially in our multiple shooting, our direct transcription, our co-location methods, this snaps right in. We already have decision variables for x at all the places, and we can just write constraints directly on x's. Okay, so that was good for, I just want to make sure I say it properly. That was already good for finding passive limit cycles. Right, so most of the examples I gave, like I said, we could find the rimless wheel, we can find the compass gate, the need compass gate. It's hard to find the periodic solution, even though we know it exists. And so it's useful for finding that already. I hope I communicated clearly. Let me say it again, though. But this is also the same thing you would do for if you have a control input and you have to design the, for instance, also for designing U of t, maybe periodic U of t, right? Those just snap right into the equations. They're just one more set of decision variables in the trajectory optimization we already know how to write. Okay? So when it was a passive walker falling down a ramp, we're good, no U required. If you wanted to make that same walking robot walk on the flat, then suddenly you have to solve for the torque trajectory over time to make that happen. And it might, for instance, act like gravity, but it might be a little bit more subtle than that. Okay, so today I want to think about control, right? So this was about planning, if you will. This is finding a particular trajectory. And then what we've been doing over the sort of pattern here is we've got more complicated systems. We figure out how to understand basic nominal trajectories, and then we can understand how to stabilize those, for instance. Okay, so let's make sure we know how to stabilize. And again, there's sort of two sets of ideas. Some of them are just about limit cycles. Some of them are about being hybrid. And they actually, they go together very well. You'll see that, and more so than even last time, there's a real good reason to have these two technologies intermingled. So I'll tell you about that in a few steps. The first idea is, how do you stabilize a Poincare map directly? So we'll say that the simplest example would be that once per step control. I'll try to tell you that story. That's the simplest thing, and it's actually a very relevant idea with the way robots are being designed today. And then we'll talk about how to do transverse coordinates, which are like moving Poincare sections. Once we have that construction, we'll understand how to do transverse LQR and Lyapunov kind of methods. And then maybe I'll just write over here. And we'll put the hybrid version back in. Okay, now I said last time that some of this hybrid, it's very clean, it works beautifully for our simple robots. It's not the way you'd want to simulate a really dexterous hand or something very, very complicated. So you might think that the lessons from today are only good for the simple cases and not for the really hard cases. We'll circle back around to that question at the end, but actually I think these are the insights you get here are relevant no matter how complicated your robot is. Okay, you might choose to do the math a little differently on a more complicated robot, but the fundamental insights are, I think, more clear on these simple examples. Questions at that level? About last time or about this? Okay. So I told you a little bit about the slip model last time, spring-loaded inverted pendulum. I'm going to tell you a little bit more because I realize that's the perfect example to tell you about the stabilization on the Poincare map. So I'll give you a few of the equations I hand-waved about last time. It's a good model to know right? We said that walking robots kind of vault over their legs like a compass gate or a rimless wheel, but a running robot or a running animal tends to have more of a springy response to the ground, and the center of mass goes down before it goes up. That's one of the definitions in biomechanics that defines a running gait. Okay, and this was meant to be one of the simplest models to understand that. So it's really, again, a point mass. Now we're going to have a massless leg, okay? Going through the ground, the leg has a nominal length, at the rest length of the spring, that's L0, okay? And we'll mark the angle that it makes here, theta. With the ground, this spring has a stiffness K, okay? Of course, gravity's going down, and I'll use XY to be the location of that center of mass. So the assumptions we make in this model are similar, but there's one essential difference between the rimless wheel and the compass gate kind of walker. Okay, So this time we say massless leg, toe, which implies that instead of an inelastic collision that loses energy with the ground, we're going to have perfectly elastic collisions. Right, so basically when the foot comes into the contact with the ground, if you have no mass there, then it loses no energy, but it starts compressing the spring as you go in. It's still an instantaneous event, this coming into contact with the ground, right? But it's just not there's not an impact there. The interesting consequence of that is that energy is always conserved. There's actually no losses, and this is hopping on a flat terrain, okay? And it's interesting to say, like, okay, you're going to tell me about stability of a system that's completely conservative in energy. That might trip alarm bells in your head, depending on how much you think about mechanics and stuff, okay? So this is going to be a system that has a stable periodic hopping motion, like we saw, up to perturbations in energy. There's nothing it can do. If you were to come and knock it and increase its energy or decrease its energy, there's one direction where you can perturb it, where it will change its stability, but the rest of the degrees of freedom will converge. Okay, so we're going to say a little bit less. But even the fact that it has that much stability was surprising to like theoretical mechanics people. They wrote papers about, oh wow, this is a neat class of piecewise holonomic systems. It's the fact that it makes and breaks contact actually makes it more stable than a traditional passive system. Okay, but the reason I want to use it today is that we're going to actually add some control. We're going to assume that we can, because we have a massless leg, there's sort of no notion of torque, and we just have a point mass here. There's really no way to think about torque here. So we're just going to say you can just angle the leg instantaneously. That's the assumption. So it's still a hybrid system. We write one set of dynamics when it's flying through the air. That's just the ballistic trajectory of the mass, right? It's just mg equals, equals mz double dot equals negative mg, right? It's just a flight of a ball because this leg does nothing. But then when it's in contact with the ground, suddenly we have a new model that we have to write the equations of how the leg interacts with the ground, right? And so we'll have the periodic solutions will have trajectories that look like this, where it compresses and leaves and takes off again. We assume that it takes off when it gets back to its rest length, okay? And we have to write the dynamics of the stance phase also. But that's easily done. These choices of making everything simple makes it also very simple to write the dynamics of that stance phase. And one of the questions Harvey asked last time was that when you're in the regime of small angles of attack here, you can just linearize that and we get like closed form solutions of the same way I said with the rimless wheel, we could actually integrate the entire Poincare map. You can integrate the entire Poincare map of the spring-loaded inverted pendulum if this angle is small and you're willing to make a linear approximation. Okay, so you can put all this together and get an interesting dynamical system. It has a stable hopping. Fixed point, which I showed you last time, and then it'll eventually fall down if you push it too far, or if it gets too low to the ground. There's a couple different failure modes. The dynamics on the Poincare map, which we can solve for, take the initial condition on the map, We tend to use the apex to apex map. Again, we talked about that a little bit last time, but it's not essential for this part of the conversation. Okay, the map goes from apex through the ground, through the stance phase, back up to apex, and it's going to be a map from the variables at one apex to the variables at the next apex. And it's going to depend on our control input, which is going to be the leg angle, and I'll call it the commanded leg angle alpha. Okay, before I show you the math of how to stabilize that, which is we're close to already, let me just tell you a little bit more of the story of the spring-loaded inverted pendulum. You know, it was initially, it seemed like a very abstract model, but what was amazing was the series of studies by Bob Full at Berkeley and a number of his collaborators, where they studied real animals, and they started asking, what is the trajectory of their center of mass relative to a virtual point on the ground, center of pressure on the ground, for instance. Okay, and it turns out that those trajectories looked sort of fairly characteristically like a spring model. That was some of the initial ideas. But what's amazing, not only do they all kind of look springy, but across a huge diversity of animals, if you do the dimensionless analysis, okay, you have to normalize out mass and stuff like this, but you get a dimensionless spring stiffness, and it's surprisingly constant from things like a cockroach, right, which has 6 legs, to a kangaroo or a human. It's sort of nuts how they found some of these invariants in the way animals move that are across huge length scales, right, of different masses and length scales. And it seems to be an interesting model of like the dynamics of how animals choose to move. There's a line of work for robotics around this that was designed, it was called templates and anchors. They say maybe actually control is simple. Our control system is just trying to embed these very simple models like a spring-loaded inverted pendulum, and the details of our links should just be whatever it takes to embed these very simple models. So this is in the sagittal plane, so if you're looking at me from the side and you're looking at my center of mass. Okay, but then another series of work said it actually, in the lateral plane, if you look at me this way, then my stability side to side can look a little bit like a spring mass model too, okay? And yeah, so I got a funny video, okay? So for instance, cockroaches, when they get perturbed a little bit like this, they seem to right themselves roughly like a spring. So there was a guy studying this. His name is Devin. He was doing a postdoc with Bob Full, and he's like, okay, he did a series of beautiful experiments trying to understand cockroach locomotion, right? And he did things like, he wanted to make force plates to measure the forces of cockroaches, which is really hard because they're small. And so his brilliant idea was he actually he found a way to make Jell-O in such a way that he could make it basically that the Jell-O would diffract the light, and you could sort of put a grating on either side. When the cockroach stepped on the Jell-O, it would bend the Jell-O, and you'd see bursts of light that would be compatible with the force. And he said it worked incredibly well, except for the cockroaches ate the Jell-O all the time, right? But his best experiment by far, he says, he wanted to understand the lateral stability of the cockroach. And he's like, hard. How do you perturb a cockroach, right? They're fast little buggers, right? And you want to do like an instantaneous perturbation. How do you do an instantaneous perturbation? He said he went through a bunch of things like tie a 12-plate string. You couldn't do it, right? So his final solution was this. This is a cockroach. You're looking at it from above. That's a cannon strapped on the back of the cockroach. They have exoskeletons, so you can just bolt the cannon to the exoskeleton. That was an explosion. This one happened, the ball bounced back and hit the cockroach, but that wasn't intended. Okay? And these things just keep on moving, okay? And one of the beautiful things in that study was that his observation was not only does the vertical view of the trajectory, it looks like it stabilized pretty quickly despite a pretty big perturbation. Okay, but actually the orientational velocity of the cockroach stabilizes like within a step and faster than they think the neural response of the cockroach could possibly be. So their strong argument was that it's actually the mechanics of the leg that are implementing spring models in order to stabilize the cockroach in the lateral direction, which is pretty cool. This is Devin's video. The other thing Devin told me, I don't, you know, I told him I thought it was funny and I might tell people. He said that's okay. But at one point when he was describing it, he said it's surprising how little gunpowder you need for these cannons. And I just think to myself, what were the first experiments like? You know, just like, well, you know, there's no cockroach. You know, but just that little statement he made, my mind went spinning, you know? Like, what does that mean? Okay, so these things are like super simple models, point masses, but they've been surprisingly good at describing things in biology and in helping robots make their things work. Okay, so let's think about how to control the slip model. Right, for our purposes, I just needed something where I had the notion of a control that was kind of once per step control. So it's basically we could think of that control action as happening whenever the slip model gets to its apex, it instantaneously changes its future touchdown angle. Okay, and so now we're in a mode where we're once per visit to the Poincare cycle, we make a control decision. So if I have my Poincare map that looks like this, you know, I can actually think of it as almost like this, right? Then what I'd like is, of course, some policy that'll stabilize the Poincare map, right? So if I have a particular y star, for instance, on the Poincare map, if I can stabilize that, that will infer limit cycle stability of the whole cycle. Okay, so here's idea one. How about we linearize P, right? We can get xn plus 1, or sorry, yn plus 1 I called it. I don't know really why I called it y there, but n plus 1 is approximately equal to and then we could do LQR. This is just a discrete LQR. It doesn't have the same connotation as the original discrete LQR we did, right? Because the time could be different on every of these time steps. It's not clocked in time. It's event-driven that you get to the top. But once we have this abstraction of the discrete map of going around the cycle once, we have a discrete system. Okay, it might be a little bit harder to call it a discrete time system, but it's a discrete system, okay? And you could absolutely do discrete LQR on that system, okay? And that actually works just fine. But there's actually something that you can do in these systems, and it's possible in any discrete system that's even stronger than LQR, okay? A continuous time system, if you want to get to the origin, you have to, maybe you try to do it exponentially fast, okay? A discrete time system can jump directly to the origin, right? Whereas a continuous time system, you have to plot your whole path and have some rate. A continuous time system, or a discrete time system does have the ability to jump there in exactly one step, okay? So that would be called deadbeat control. Where if we have it, that says that basically y1 equals, well, more generally it's y star for any y0. And what's amazing is that for these slip models over a wide range of parameters, the Poincare map is monotonic in a way that can be inverted effectively. And you can solve for u such that pyu equals y star. And this has a nice, unique solution for the spring-loaded inverted pendulum model for a huge range of initial conditions. Okay, so what does that mean? I'm hopping along, and I want to get to a new hopping height. I can choose a leg angle so that in exactly one step, I'm going to be at the new hopping height. Okay, that's a unique thing that we can do because as we've gone to the discrete abstraction. We have time over the trajectory to make that, over the cycle to make that happen, but we can choose an angle, and using just analyzing the Poincare map like this, we can solve that problem. Okay, in the slip model, the action is just one variable, so you can just brute force find the minimum, or golden section search or whatever. You can just do a brute force search. More generally, you might try to solve an optimization problem in higher dimensions to do that. Is that clear? So these two ideas are kind of a class of control, of ways to control, let's say, a legged robot or a periodic system where you're deciding once per step, and that can be very powerful. Okay? It can be enough if your actuator, depending on what your actuator is capable of, that might be all you get to do, right? So I know there's folks here from Harvard RoboBees kind of project. You know, these are super fast flying flappers, and you don't get to make lots of control decisions per flap, right? In fact, they're actually in the other regime where they're making control decisions less frequently than they flap, typically. Okay. It turns out there's something even, there's a result that I just think is so cool. Yes, please.
Yes, I guess are these two techniques only applicable to these slip models, or can they be used to stabilize any sort of model?
The statement of linearizing a Poincare map is valid for any system. You could write an LQR controller. You could ask, just like for any linear system, you could ask, maybe it's stabilizable, maybe it's not. Okay, but for the stabilizable linearizations of Poincare maps, I would expect this to work in high dimensions for any sort of system. Getting a closed form solution of P is not always possible. We'll develop some of the tools to get around that. The deadbeat control is more of a property of the system. It's not so narrow as that it's only for slip, but it may or may not be possible for different systems. Slip has enough, it's even more so than stabilizability. You have to have enough authority to be able to get your system to zero in one step. The slip has it. Many systems have it, but I would say less than what LQR is good for. You can't always achieve that. That's a strong requirement on a control system. Okay, there's one super cool result. I won't go too much into it, but I want you to have heard it, okay? For slip models running on rough terrain, so imagine that I've got my little slip model like this, okay? The terrain's just changing in some maybe simple to model way. It doesn't have to actually be that simple. And let's say our goal is to keep it hopping at a certain height. Okay, it turns out that this solution of the optimal touchdown angle is actually monotonic in the desired hopping height. Okay, so what does that mean? So that means that if the terrain is here, there's a particular angle that I need to put my leg at to get back to this height. If I lowered it a little bit, my leg would be a little bit like this to get back to the hopping height. If I lowered it a little bit more, then I'd take a slightly steeper angle, but it's a smooth set of angles, okay? So what happens in this particular setting, this one is specific to slit, okay? It turns out you don't even need a sensor to tell you where the ground is. If you just close your eyes and go through a sweeping motion at the schedule that you're falling, then whenever you end up hitting the ground, you'll be at exactly the right angle to get you back where you wanted. Of course, up to the regime. If you go past vertical and stuff, it stops working. But in a pretty big regime, you can just close your eyes and sweep at a certain angle, and wherever you happen to hit the ground, you'll bounce back up to that in a single shot. Okay, so it's a deadbeat control for slip on rough terrain, blind, right? It's pretty cool. And Hartmut Geyer is the one who told us about that and has these nice videos of it doing exactly that. Okay? Yes?
When you say sweep at a certain angle, is that at a certain rate? Your leg is at a certain
Exactly right. So you know, because you're just a ballistic trajectory of your center of mass, how fast you're falling, right? So you know that gives you the rate, right? So you want the angle whenever you hit the ground to be lined up, so you sweep it at that rate. Yes?
And that's ignoring any like possible collisions or anything?
The collisions are idealized, right? Oh, you're saying, I see, if you were to bump yeah, exactly. Yeah, this is just saying I came in clean, and if I were to bump my toe or something like that, the model doesn't capture it. Yeah, that's good point. This particular image sort of makes you think that, right? You could have clipped his toe or something. Yeah, you kind of assume that our leg isn't there and it reappears at the end. Which sounds crazy, right? That's like, okay, that's just a little, there's a joke about how theoretical physicists say assume a spherical cow, right? Actually, Andy Ruina likes the joke. He says, spherical cow is way too complicated. You need a point cow, right? Okay, and that's fair. But actually, the robots that people are building these days, right, have super light legs and almost massless feet and can move their legs almost instantaneously. Okay? That's sort of what made quadrupeds work so well, right? So it's not that far. I mean, of course, there's still inertia in the legs and things like this, but these robots are often in the regime where they can move their legs almost instantaneously, okay? And that makes them very robust. Yes?
Theoretical ideas like this, that just do the sweep motion regardless of the terrain, will be able to move, make you think that it make it sound like locomotion is easy, but then in reality it's not. Where is the disconnect?
So
Is it real?
the question is, this makes it sound like locomotion is easy. In reality, it's not. Where's the disconnect? Is it that hard? I mean, maybe it's easy, right? I mean, I think we made it hard for a while. But things are working. A lot of different things are working well. I think there's regimes where locomotion should be easy, right? This is highlighting it. I do think there's gaps. I think real actuators don't do instantaneous leg angles and stuff like this. But in that regime, that sweet spot, I think control does become easy. In fact, a lot of the, there's different mechanisms for stability in a legged robot. One of them, of course, is regulating angular momentum and regulating your torso and things like this. But foot placement, your choice of foot placement, is a dominant mode of stabilization. And I think that's really what happened. Is a lot of these robots got to the point where they could move their legs so fast that they could place their foot arbitrarily, and that makes things locomotion a lot easier. It used to be some of our early stability metrics in legged locomotion were dominated by the most important time constant was the swing leg speed. How fast can you move your leg, right? Because that's what gives you the ability to do foot corrections. There's still things that are hard. I mean, it's a pretty good, if you ever want to test someone's humanoid controller, right? You see all these amazing videos of step recovery and, we've done it, but you rarely see videos of someone coming up and pushing the robot this way where it has to step across. That's a lot harder, right? There's tricks. There's things that are still hard, right? I think people can do that now, but for a long time it was like every robot video I ever watched, they were being pushed this way. It's not just chance. I've got one more story on this. The legs are so good. So horses, right? It's actually really interesting how horses work, right? So horses throw their legs forward faster than you would expect them to be able to based on the musculature in their legs. Like muscles don't contract that fast to be able to move their legs that fast. And it turns out, I'm not a biologist, but I've talked to biologists and I'm probably corrupting their story slightly, but there's a tendon that runs around the hip and down the leg, okay? And what they're doing is in the stance phase, they're actually loading up a big catapult, basically. And then when they lift their legs up, they're shooting this off with the passive tendon accelerating it faster than the muscle could possibly do in order to get those super fast swing speeds. But swing speed is a major dominant factor in a lot of the locomotion stuff. Yeah?
Is there like a limit to like how big those steps can be, like linearization of their skirt?
Oh, good. So the question is, what's the linearization on this? What's the limit on the steps? Yeah. So I mean, there are limits to how just even if you're flat, you have a constant energy system. So there's only a maximum height you could possibly achieve. You'd end up going straight up, and then you'd have no solution to the return map. And so that would be the same as how low you could go. The map you compute here, the way you invert it, if you used the P that was designed analytically using the linearization, then you would have a small angle limitation. But you can actually, this is so simple, you could just compute it by simulating if you wanted to, and do the exact P and get rid of that particular limitation. Yes?
Are there ways to limit the required swing speed so you can use methods more like a passive dynamic walker?
I think, so the question is about, maybe these swing speeds approaches are not compatible with the story about beautiful passive dynamic walking. Is that right? Yeah, that's a good question. I mean, I think when people said, what's the minimal thing we needed to add to a passive dynamic walker to make it more stable? This is partly where the questions came up. You might think I'd add a little bit of hip torque, for instance, right? But that's actually not, the ability to place your foot is actually more important if I were to pick one actuator to add. For stability, it tends to be, I'd want to be able to choose my foot placement. That's a more powerful in most of these regimes. And I think it's still, you don't have to do it quickly to use that as an effective stabilization mechanism. Yeah, I think you're right that like super fast foot placement, that's beyond passive dynamics. Yeah. All right. So that's one idea. That's point one. Okay, good. That's the once per step control. And I want you to understand that I gave it a simple example of that for the slip model, but that's true of any Poincare map. You're setting up a discrete map. Or if you even had maps that went from like in a mode sequence, I went from impact 1 to impact 2 to impact 3, I could still design, let's say, a with time abstracted, varying linear dynamical system and do LQR on the once per event control decisions. And that can be very powerful. But of course, you can do better if you're willing to make control decisions throughout the cycle. So let's think about how to bring our tools over to that. And the first thing to do there is to give you this idea for limit cycles of doing transverse coordinates. Okay, so let's think about stabilizing a limit cycle for even a smooth limit cycle. I'll just reset just like we did van der Pol and then we did added hybrid. Let's think a little bit about just smooth dynamical systems, right? Maybe one of the simplest things, let's even analyze stability of a smooth limit cycle with this kind of a approach. So I can write a very simple oscillator, maybe just a ring oscillator even. Let's say this is a limit cycle that just goes around in a circle, and I can write this trivially by saying, if I write it in polar coordinates, okay, right, so something like that, yeah? Okay, so if I have this sort of a dynamics, I've chosen this to be stable around the limit cycle. I put the 0 here at when r equals 1, and I have kind of a vector field that brings me like this, Okay, so before we stabilize, let's just make sure we can understand the stability using these tools for a stable limit cycle, a particularly simple one. Of course, we could use a Poincare map to do this. All right, but I want to develop the next tool, which is now a moving Poincare map. Okay, that's just going to move along the orbit. And think about the dynamics on this moving Poincare map. Because then I can have a dynamical system that evolves over the cycle, and I can make control decisions that influence that Poincare map. Okay, so we're going from the original Poincare map to a moving Poincare map. Poincare section, I should say. Okay, so I'll define a Poincare map at some particular tau or some particular theta. Okay. In general, for these moving sections, I could use theta and r, but let me just write it in the slightly more general notation. Okay. Because we'll use it for all our systems here. So if I call the angle across here tau for my phase angle, and I'll call x perpendicular my transverse coordinate, which in this case is r, okay, but it's my coordinate along this section. Now in higher dimensions, of course, tau is going to still be a scalar, even in high dimensions, but x perp is going to be n minus 1 dimensional. Whatever x, the full dimension is, I'm going to have one less than that for the transverse. Now the word transverse is important here, okay? Just like the surface of section, what we wanted is that the flow, it was transverse to the flow, that all of the flow always went through the moving section, as opposed to any flows that could possibly like take a glancing blow on that section. We want it to always penetrate the section. It doesn't have to be perpendicular to the orbit, but it just needs to be not parallel to the orbit, okay? Then we can make this sort of moving coordinate system that as a function of tau, I have a different mapping from x to x perpendicular. But that's a function I could pre-compute around the nominal limit cycle. And then I can ask, what are the dynamics of tau and the dynamics of x perp? Okay. For some particular system, I can just separate the space and write it in this coordinate system. That's not anything new to limit cycles. I could do this for any system. But I'm just going to choose to decompose the dynamics into those components. A scalar phase and a vector perpendicular. Yeah?
Could you explain what x perpendicular is?
Yeah. So in this example, it's r. It's just the coordinate along here, right? So this is x perpendicular equals 0. This is x perpendicular equals 10, right? And in a higher dimensional thing, think of an entire plane that I have a little trouble drawing on the board, but if I had an entire surface of section that was somehow moving along the coordinate system, I could write some coordinate system on that plane or that hyperplane, and as long as the trajectory doesn't glance through but always punctures it, and I've got a transverse coordinate system. Okay, what's amazing is that the notion, this construction is exactly what you need to think about orbital stability, right, of a cycle. Remember, the standard notions of stability for a lot of our limit cycles would fail. Like, two trajectories do not converge in the full coordinate system because they might never converge, they will likely never converge in tau. Limit cycles don't do that, okay? What we'd like to do is create a Lyapunov function, for instance, that lives just in x perp, and say as long as I converge in x perp and the dynamics of x perp are defined like this, okay, then I can have a Lyapunov type argument that talks about the stability in an orbital sense. So the picture you should have in your head is something like this. We want to construct a Lyapunov function that is like a bowl, but it's 0 on the orbit. Okay, and all we'd like to say is that states that are off the orbit will move down that bowl. Okay, but we don't say anything about what's happening along the cycle. And it turns out you can do that, right? So it becomes a standard Lyapunov argument, and with a little bit of work, that other people have done to talk about the rigorous Lyapunov arguments, we can say that as long as our system has a few certain properties, that we can guarantee orbital stability by having a Lyapunov function. So if I can find a v of x perp tau, okay, such that for all tau, I have v of x perp tau is greater than or equal to 0. Okay, so I'm just meaning this positive definiteness for the x perp component, and it's got to be true for all tau. Right? And again, for all tau, v dot x perp tau is strictly less than 0. For all x in a domain, you can't have global, but you could talk about this locally, you could talk about this over some region. Okay, all of the same Lyapunov methods apply. But if you can say that the system is only decreasing in x perp like this, then that is equivalent to x perp equals 0 is locally or regionally orbitally stable. In this case, when I wrote it like this, it's orbitally asymptotically stable. And again, you can do the variance, you could do the exponential version, you could do the stable in the sense of the Lyapunov version. Okay, it's exactly what I said in that picture, which I hope snapped into your head immediately. I'm just writing that quickly with the scratching the equations, okay? But that's the same statement. If you can find a Lyapunov function that's going up away from the orbit, and the time derivative is going down, then you can say that infers orbital stability of the 0. Okay, so how does that play out on the ring oscillator? I decided to just pull this up. It's in the notes here, okay. But in the ring oscillator, if you just use the atan, I guess I've missed a negative somewhere there. Negative. Okay, if I define my coordinate systems just like I said, okay, then in that transverse coordinate system, tau dot just equals 1, okay? But what matters is that x perp is negative alpha x. And a simple Lyapunov argument, a simple x perp squared is enough to certify that in the region around the attractor. Yes?
Does this approach, is it restricted if the shape of your cycle is kind of like wavy or blobby?
Oh, good question.
What would you do in that case?
Okay, so we definitely have seen a more curvy van der Pol oscillator, right? You could choose things that go directly out from the origin and maybe be okay, but it could be, you could find systems where that might be hard. But I would still, what we tend to do is we actually can potentially solve an optimization problem to find nice, smooth surfaces of section that move along. And it's not hard to find them that are sort of consistent, okay? But finding the one that will give you the biggest region of attraction can be a hard question. Yeah. Oftentimes it is better to locally try to find a good, a good transverse coordinate rather than just picking a global one because of the curviness of the trajectories. That's a good question. Okay, so why is this useful? Oh yeah, sorry.
Sorry, does it have to be the same Lyapunov function, or
you need the proper statement talks about the smoothness of the function and things like this. You want it to be a smooth function of x perpendicular and tau, okay? So you need a smooth warping of this bowl around as the system moves. You know, and the x perp coordinate system has to be a smooth changing thing. Mostly smoothness is the big requirement. Yeah.
If we have a point, like looking at like the Van der Waals oscillator one, you have a point sort of in like the top right corner where it's not clear which coordinate system you would think of it as being a member of.
Yep.
Can you pick one, or does it need to be true for every coordinate system?
Yeah. So this would tend to be a limit of when we start doing region of attraction analysis. Any singularity in the transform is going to put a upper bound on the region we can certify with that particular choice of coordinate systems. Right, so maybe you could do something more clever there, but I think that gets pretty bad. So we just say, you know, our sublevel set is not allowed to be bigger than the place where those things, you get a singularity in the transform, in the projection. Okay, so let me just try to make sure that I land why this is a useful construction. Okay, so it's going to be useful for control in a second, but it's actually already useful for just making stability arguments of limit cycles. The Poincare map is amazing, but it has an assumption baked in, which is that you can come up with this P by integrating around, and very rarely can you actually get a closed form solution for P. So if you wanted to make a rigorous argument about stability, it's hard. You tend to only be able to do that numerically. Here, you can certify the conditions instantaneously along the entire trajectory and use, you know, proper, you can, sums of squares still has, you know, you have to talk about numerical limits of the sums of squares solver and stuff like this, but you can do a sums of squares argument along the trajectory, okay, and put bounds on errors and things like this, and without having to solve for a closed form solution for the long-term Poincare map, you can make a stability argument around the cycle. Is that clear? The V dot conditions I'm checking here are instantaneous. They just use the instantaneous dynamics. X dot equals f of xu, right? Or f. Let's say. Whereas if I wanted to make a statement, talk about a Lyapunov argument on the original Poincare map, I would need P. I would need the integral across the entire cycle. That integral is hard to get for nonlinear systems. The instantaneous object is much better to work with. Okay, so how do you find Lyapunov candidates? Well, it turns out there's a natural object once you've defined the transverse coordinate systems, which is the transverse linearization. I should say this one is approximately this. You can linearize those dynamics. When you have a tau involved, they tend to be time varying. But you can come up with a linearization of that nonlinear dynamics in the coordinates. And then you can solve Riccati equations and eventually control directly on that coordinate system. Do it over here. So you remember for the simple case, x dot equals ax, I had a Lyapunov method just says find me a p greater than 0 such that p A plus A transpose P equals negative Q. This was the original Lyapunov method. And this is to find a Lyapunov function the transverse sort of periodic extension of that is I'm going to find Vx of tau is going to be x perp V P of tau x perp, where I want P of tau to be greater than 0 and I use the Riccati or the Lyapunov difference equation Okay, so what I said here, this is just a natural analog to that. That's just the time-varying version of it, just like we went from LQR to time-varying LQR. We have Lyapunov to time-varying Lyapunov. We'll have the same thing, and now this is in the transverse coordinates, okay? And what we want to do is we want to find a solution to this Lyapunov differential equation that is a periodic solution. We want to find one that's like this. And there's people that have done a lot of good work on the right numerical methods to find the periodic solutions of this differential equation. In practice, I just integrate it backwards over the cycle a bunch of times until it converges to almost something that's periodic, which isn't guaranteed to work for every system, but every system I've ever tried it worked for. There's theorems saying that won't work forever, but it's fine for me. Okay, I don't want to get lost in the weeds of that, but I hope, does the idea sort of clear? We had natural methods just using linear dynamics to come up with quadratic Lyapunov functions. And they extend to the time-varying case, and we're going to use them just on the perpendicular coordinates. And we get our beautiful bowls, our beautiful quadratic bowls around an arbitrary limit cycle. And that gives us an initial guess. And then from there, you can do sums of squares, for instance, along the cycle to try to estimate the region of attraction of the limit cycle. It's pretty good. Questions? You guys don't look completely happy, so. Thumbs up or thumbs down? Is it kind of a lot of angle? It's thumbs, yeah, somewhere, okay. All right, that's good. Thank you. Okay, I accidentally wrote BU already in my transverse linearization, but that's obviously where we're going, which is the same way we can do local linear analysis of that on the transverse coordinates. For Lyapunov design, we can do LQR on the transverse coordinates. Okay? So what does it mean to do LQR on the transverse coordinates? Done. Okay, so if my x perpendicular dynamics can be approximately turned into then this is immediately a time-varying LQR problem. We did it previously over a finite horizon. Now we want to find a periodic solution. Okay, we want to find a periodic solution. U equals negative k tau of x perpendicular. And we get this by solving the same way we did the periodic Lyapunov equation. We just do the periodic solution of the time-varying LQR Riccati equation. So you just solve your LQR problem backwards over the cycle. Maybe you have to do it a couple times until the S's and the K's converge to a periodic cycle. And now you have a periodic Lyapunov function and a Costa-Go function and a periodic controller. Now if you want to execute that controller, you need a tau, right? So you can just, at runtime, find the closest tau to your current trajectory, use that tau, which defines all of the projections, and gives you a lookup into this controller. Okay, so that's the machinery. But let's just talk for a minute about why this is a good machinery, okay? So as we're moving along a cycle, understand that we're going to have a current state. We're going to find the closest point on the cycle. We're going to look up the coordinate system based on that. We're going to take a controller that's trying to move us back. That's a good controller in the sense that if you were to push me along the cycle, it's not going to try to slow down. You know, if you're to push me or hold me back, it's not going to try to speed up. It's only stabilizing orbitally. It's not stabilizing in the full coordinates. You could try doing LQR on the full coordinate system and just taking this and saying, I'm going to just do this in the full coordinates, okay, and then choose a tau. But that's actually not guaranteed to be stable. You could, because you're in here, you know, like changing time on this controller that carefully you told it could believe itself, you know, it could believe some time dynamics. The transverse LQR is exactly the LQR controller that is safe under perturbations along the orbit. So in that sense, it's the right construction. Of course, you have many choices of what transverse coordinates you pick, but it's natural to try to do that if what you want is orbital stability. Even for a trajectory, for something like perching or something like this, maybe you don't want to slow down or speed up. There are times where using a transverse coordinate of even a finite horizon trajectory can be a better objective. There's also times where it can be worse objective. Okay, but for orbital stability, this is the natural objective. Yeah.
And this has to do with the fact that it's perfectly perpendicular to the trajectory, right? Like if it's slightly off, there's going to be a little bit of it would be affected by perturbations.
It does not have to be perfectly perpendicular. When I'm writing transverse, that is as opposed to writing perpendicular. So transverse just means it's not aligned. So what happens in the case where it's like slanted or even changing at an angle faster than, so then the dynamics that you write of how x perp evolves as a function of, I guess I forgot my tau here. Okay, as a function of x perp and tau, okay, this, that has to capture the rate of change of your coordinate system also. Yeah, so you could change, as long as it's changing smoothly, that's okay, and that falls into F, if it's, you like it to be that the linearization is good, so if it's changing crazy, if it's, it doesn't even have to be a linear map. It could be some crazy coordinate system like this, okay? But you want the linearization to be good for as long as possible for the linear type control to work. Yes?
Do you have to put thought into choosing the transverse section or whatever so that you have like more control authority in that particular section of something?
Yes. So I think your success, the performance of your controller, even the size and certainly the regions of attraction will depend on your choice of coordinates. Yeah. You would like to think that if it's mostly perpendicular or something, you'd be pretty close. Okay, there's actually a subtle point here too, right? So if I have, let's say, a compass gate walking robot, okay, and I have one controller, let's say I put a torque at the hip. Now I have, two leg angles, one actuator, under actuated, cool. All right, so if you try to stabilize the thing completely in time, actually if you looked at the controllability gradients and the like, you realize the hip doesn't have much authority to control the leg, the bottom toe. It's actually just weakly controllable in that sense. Asking it to stabilize, designing an LQR controller that's trying to be in the full state, you might be able to find one, but it's going to have really big gains because it's very hard for that system to move along the trajectory, even though there's an actuator that a chance it could push itself along the trajectory, but that's very hard for the hip actuator and the compass gate. So in practice, going from the full coordinate system to the reduced coordinate system, you get back to beautiful small gains, good performance. Okay, maybe one other thing to say here is that that if you were to, I forgot what I was going to say. But what point was I going to make? It'll come back to me in a minute. I'll show a video and that'll come back. So what does orbital stability look like for a biped? Let me just show this one thing and then I'll answer questions. This is Jesse Grizzle at Michigan. That's not Jesse, that's one of his students, but this is Michigan Walker. Oh, I should have done that. Yeah, if I had started it exactly where I'd left it. Okay, so true orbital stability in this sense, their controller is actually, it's not even doing LQR, it's just doing a simpler joint-based control using something called hybrid zero dynamics. But it's the way, what it's doing is it's imposing orbital stability on the walking robot, okay? So much so that he can just back it up and it's like pulling it backwards around the limit cycle, okay? He's just projecting back. It's basically you've made a clockwork man, right? Where it's just, as a function of the bottom leg angle, there's a prescribed set of angles for the rest of the robot, okay? So it's no matter what that is, and you just walk it forward or backwards. That's what orbital stability looks like.
So
Yeah.
the controller's active the whole time, even as he's bringing it back?
Yep. So what it's doing is it's saying, as a function of my, let's say, ankle angle, what are all the other joint angles? And you get this beautiful stability out. Yes? Should have known better to leave it running, yeah.
Is it always a property of a cycle like this that it's stable if you go backward?
No, sorry, you're right to catch me on that. So in state space, and it actually, you can't go backwards in the state space, right? So this is a particular case where he could write the entire transverse coordinates, if you will, and achieve the orbital stability by clocking all of the other angles off the one angle. Okay, it's a sort of, it's extremely clean in the 1 degree of under actuation case, where you have like 1 point angle that's unactuated and the rest are actuated. There's generalizations that Jesse and his group have worked out for higher degrees of freedom, but it's super clean in that case. In this case, in the Q coordinates, you can go backwards and forwards, right? Yeah. Yes?
I guess question about computing tau. Like, I feel like if you did that, it would be sensitive to like unit CPUs, so you could do like big reads versus like medians. I was
So tau is often time, and tau dot is often 1 on the cycle. That would be a natural choice of coordinates would be one where tau dot is just 1 and it evolves with time. But I mean, in any choice of these optimization problems, changing coordinates can change, especially if it changes nonlinearly, you can change the way that system looks. But I would say degrees works in some of the simple examples, but typically in higher dimensions, we just think of it as time along the cycle. Which is defined as 1 on the nominal cycle, but it might evolve kind of less than 1. You know, it's not time anymore once you're off the cycle. It's time on the nominal cycle. Okay, one last idea to land this. So we can do LQR to stabilize a limit cycle, but I haven't told you how to deal with the impacts, right? That most important picture of how to, think about, we've got a guard and a reset. How do we do LQR? The orange is not significant. I just ran out of white chalk. Just there. Okay. If you think about the challenge of designing even a linearization through an impact, we know how to sort of make local. I could summarize this as x dot is approximately, ax t I could summarize this in the smooth dynamics with my existing linearizations, right, on both of these sides. But something more complicated happens here. In particular, there's lots of squirrely cases, okay, where if I were to clock everything off time exactly on the nominal trajectory, let's say I've got a slightly perturbed trajectory. The time that it actually hits the guard and resets could actually be different, right? So if I were to design my original time-varying LQR controller through a hybrid impact, and I came up with a k as a function of time, I could find myself in a situation where the nominal trajectory had an impact. It says start using the A's and B's over here, but the actual system lagged behind. So the gains that I could use here might be a very wrong gain to use over here. Did I say that well enough? Right? If you just clock your gains off of time on the nominal trajectory, you might be sad, right? And this happens in experiments. I bet it happened in Marlow. I know it better in the ones, we had an old compass gate walker in our lab here, okay? So this had actuators in the toes, right? This was the first version of it that you put blocks down so you don't have to worry about the toes scuffing the ground, and it's got an extra leg, okay? An old version of a compass gate biped. But one of the things that happened in that model was, if you think about just even it also had a hip torque, okay? What happens is that the thing you want to do right before your foot hits the ground is to apply a particular torque, in one direction. The thing you want to do after you hit the ground is exactly the opposite thing. Like the gains on your hip torque change dramatically at the moment of impact. So it was a real pain on this thing to try to estimate when the foot hit the ground. And if you got that estimate wrong, it would be almost catastrophic. It would be like the robot was coming down, it would go, and then bam. Then it's really a problematic thing. So people have done a lot of work in Liget robots to try to estimate contact times and to try to smooth out the gains through contact intervals, right? Because you don't want to be highly sensitive to that estimation. out of the box, LQR, time varying LQR, would be highly sensitive to that estimation. Okay? You can do slightly better. This doesn't solve it, but you can do slightly better if instead of doing LQR in the original coordinates, you design a transverse coordinates. This time you put an additional constraint on your transverse coordinates that you'd like it to line up with the guard at the moment of impact, and similarly on the way out. Okay, then you at least expect your LQR gains that are safe under projection along here to be correct if your state estimate is correct. Okay, and then you get robustness through this contact. In practice, even that depends on knowing and estimating the state of the robot, and that can be sensitive. So there's a lot of work to try to make those gains go. I mean, intuitively, what you want to do is have those gains almost go to zero if the goal is to go in the opposite directions on either sides of the impact. The formal way to achieve that is to talk about robustness with respect to the uncertainty in your state estimate or uncertainty in the guard position, which will then drive the gains to be zero in an optimal control design. Okay. Sometimes people just turn the controller off when it's close to the ground. I hate to say it, but it happens all the time, right? You like have this beautifully designed theoretical controller, and then you right when you're close to the ground, you're like, just turn off the control for a second, let it go through, and then okay, well, run again, because it takes a lot of work to get robustness back out. Okay, so the transverse LQR is actually exactly the right way to do LQR, hybrid LQR, with the additional construction of that you can line up your transverse coordinates with the switching surface. And that is why, like I said at the beginning, doing the construction for limit cycles and doing the construction for hybrid goes sort of wonderfully together. The original construction was motivated by orbital stability. It gave us these transverse maps, transverse coordinates, but it turns out to be exactly what you need to line up with a switching surface. So in practice, when we've done things like sums of squares to estimate regions of attraction of, let's say, the nominal limit cycle on the rimless wheel, this is one picture. This is kind of the zoomed in view of the eyeball, right, with the orbit along the top there. The upright configuration is here because the ramp makes it shift it to the side. And the nominal limit cycle goes like this, bless you, and then has an impact and goes back, okay? The true region of attraction is the light pink, and the sums of squares region of attraction is the purple. It's a nice big, region of attraction estimate in the vicinity of the true limit cycle. The same way we'd expect our LQR regions of attraction to be inner approximations, and you hope that they're big inner approximations. The same thing can work for limit cycles. Yeah?
What if you don't really know what trajectory you want?
Yep. So the Lyapunov-based tools out of the box want to know where zero is. Yeah. There's a related set of tools based on contraction analysis, contraction theory, that just ask that trajectories locally are converging, and if that property holds over some interval, then you don't actually have to know where the zero is. They're slightly harder to work with numerically, but people have had a lot of success with these contraction metrics, control contraction metrics. I have some citations in the notes for it. And this is the estimated region of attraction of the compass gate. Okay, the gray region. One of the original ones. It was hard to plot the high dimensional system with projections and everything like this. But nominally speaking, it's not surprising maybe that the regions look bigger for the swing leg, right? And this is the stance leg being like the rimless wheel. Yeah?
What does it change if the gamma is greater or smaller?
Yep, it will have an effect. I mean, this is all for a particular set of mass and everything like this, right? So you can change that around, and this was even for the passive compass gate, I should be clear. Control can make this much bigger and the like. Yeah, even the shape of the trajectory will change on the slope. Yeah. But I think this is fairly characteristic, right? I think that we do see convergence from a reasonable set of initial conditions. The numerics of these problems are pretty good. So I think for any choices that you can find stable limit cycles, you can find something that's going to look a bit like that. Okay, just to oh, sorry, go ahead.
Could you review again, like, the complications that arise from parameterizing your LQR gains based off of state rather than time?
Sorry, I'm sorry if I said it like that. So if it was a function of the full state, then you would have a time varying A and B matrix, yeah? And the problem is that at a certain time, the dynamics on your nominal trajectory could be very different than the dynamics on a perturbed trajectory. So if we do it on the transverse coordinates, it's not absolute time on the nominal trajectory anymore. We now project back, potentially through this, this mapping, that's min over tau, wherever I wrote that, right? That extra power of doing min over tau gives you the ability to sort of say, like, I'm closer to, I'm on this side of the cycle and I have a gain ready to go, right? The ability to be safe under projection of, I can, the K you get from full LQR must evolve at the original time in order to have guarantees on its performance. The transverse coordinates, where tau is projected to the closest point on your trajectory, is safe under projection along the orbit. So it's okay to slow it down or speed it up. And so in the case of, like, the perturbed system had a premature impact, it's okay to keep using the gains here until the nominal trajectory gets over there, right? And if same thing for a delayed impact. It gives you the recipe for continuing to use the correct gains and not just evolving blindly in time. Okay, so let me just say again what I said at the beginning, and I promised to say at the end, which is that I think the math of hybrid guards and having a different hybrid mode for every possible contact pair and sticking and slipping and all this, that will blow up in bigger problems. But really, if you ask even a big system, in your RL controller or whatever, right? If you're asking a system that is capable of being stable on a limit cycle, but you ask it to stabilize itself in time, for instance, you're going to get much worse gains. No matter how you model contact, right? The natural thing for most of these periodic systems is to not try to be stable along the orbit. LQR, is on the transverse coordinates is a very natural way to do that. It's not the only way to do that. You could hide it in a more complicated objective that you're solving with RL or anything. Those lessons still hold, right? If you have a stiff contact model, that's a stiff spring in some simulator, for instance, and you're trying to take gradients through it, all the lessons of sort of thinking about it as a jump discontinuity are just like very good numerical recipes for avoiding the stiffness in your differential equations, right? So those ideas do scale, right? The picture doesn't. It gets too many faces, too many possible contacts, right? The region of attraction gets a lot harder, but the basic concepts hold. Good, okay. See you Tuesday.